quiz. Which element is most likely to show many oxidation states? Zinc, scandium, manganese, or calcium? Keep your pick in mind. We'll reveal the answer in a moment and explain why. In this video, we'll explore why D-block elements show variable oxidation states and how that compares to non-transition elements like many P-block elements. Here's the big idea. Transition metals can use both their outer 4s electrons and some of their 3d electrons in bonding. Because those energy levels are relatively close, they can lose different numbers of electrons in different reactions. Across the first row of the transition metals, the ends are boring and the middle is busy. Scandium is mostly +3. Zinc is mostly +2. But elements in the middle often have several common oxidation states. The ends of the series have fewer options. Scandium doesn't have many extra electrons to share beyond reaching a very stable arrangement. Zinc, on the other hand, tends to form +2 because that leaves a completely filled D set, which is also especially stable. In the middle, you get more flexibility. These metals can lose 2 electrons, or 3, or sometimes more, depending on the reaction conditions and what they're bonded to. That's what we mean by variable oxidation states. Let's use manganese as a classic example. It can form oxidation states from +2 up to +7. +2 is common when it loses mainly the 2 4s electrons. Higher states happen when more electrons are removed, including from the 3d set. Here is a common misconception. Just because an oxidation state is possible doesn't mean it's preferred. Many transition metals have a highest oxidation state on paper, but in real chemistry, a lower state may be more stable and show up more often. So far, we've learned that transition metals can use both 4s and 3d electrons, which creates multiple possible oxidation states. And the pop quiz answer is manganese, because middle transition metals usually have the widest range of oxidation states. Want to lock this in? Your personalized practice test and flashcard set are all waiting for you. Tap the link and give yourself a quick check. Now let's deepen the pattern. From scandium moving toward the middle, the maximum oxidation state generally increases because there are more electrons available to be involved in bonding. But from iron to zinc, higher oxidation states become less stable, and lower ones, like +2, become more common. Take iron. It can form higher oxidation states in certain compounds, but in many everyday reactions, iron 2 and iron 3 are the most stable and common. That's a sign that, later in the series, the d electrons are less willing to participate. Another contrast. Transition metals often differ by 1 unit between common oxidation states, like +1 and +2 for copper, or +2, +3, +4 for some others. In many P-block groups, common oxidation states are spaced by 2 more often. And there's a deeper difference in stability trends. In some P-block groups, heavier elements prefer lower oxidation states because the outer s pair tends to stay inert, which is called the inert pair effect. But in many transition metal groups, higher oxidation states can become more stable as you go down the group. A simple way to picture this is orbital size. 3d electrons sit closer to the nucleus and can be held more tightly, so they may be less available for bonding. 4d and 5d orbitals are more spread out, so those electrons can be more available, helping stabilize higher oxidation states in heavier transition metals. To recap, transition metals show variable oxidation states because both 4s and 3d electrons can take part in bonding. The middle of the series usually has the most options, while the ends are limited. Compared with p-block elements, d-block oxidation states often step by 1, and stability trends can differ down a group. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.